Hey everyone, I'm going to start this video off by asking you to consider a question. What is 3 to the power of negative 5? This is a well-defined quantity in math, but it doesn't really seem to fit into our conception of exponents as repeated multiplication. For example, we can define 3 to the positive 5 perfectly fine. This is 3 times itself 5 times, so repeated multiplication. 5 times. And in general, we can define some base x to the power of some positive whole number y. Perfectly fine. That's x times itself y times but when we try to let our exponent be negative, say y is equal to minus 1, minus 2, a negative number, or 0, this concept kind of seems to break down. I mean, what does it mean to multiply something by itself negative 1 times or 0 times, right? What does it mean to multiply 3 by itself minus 5 times, like we're doing up here? So at first, it kind of seems like the expression I've written up here, 3 to the minus 5, can't possibly have any meaning, and that exponents or exponentiation only works when the exponent is positive. However, this is where something called generalization comes in. And generalization is something that comes in a lot of different areas of math. It's what we do when we take this concept that is basic but has a narrow scope and extend that basic concept so that it's a little bit more complex but also works on a wider scope. Now, we don't pick some arbitrary way to do this. We don't just make something up with no reasoning behind it. There are sensible and nonsensical ways to do this, and the sensical ways always preserve existing patterns that are true about the basic concept. So let's see how this applies to exponentiation. We have this basic concept of repeated multiplication that has a narrow scope of positive whole numbers, right? And we want to widen this scope so that it works for all whole number exponents, including 0 and negative numbers. So all that's left for us to consider is what existing pattern we're going to use to do this. The pattern is adding exponents is the same as multiplying the results. For example, 3 to the positive 5th power times 3 to the positive 2nd power. Well, that's equal, just by expanding out the exponents, 3 times itself 5 times, times 3 times itself twice, which is the same as just 3 times itself 7 times, right? Which is 3 to the power of 7, which is 3 to the power of 5 plus 2. So the exponents add. And in general, if you have some base x to the power of 1 power y, and then you multiply all of that by the same base x to the power of z, that's equal to x to the power of y plus z. By the same logic, you can imagine expanding out x to the power of y as some expression like this, x to the power of z, and then you mush it all together and you're multiplying x by itself, y plus z times. Now, before we use this pattern to look at negative number exponents, we're going to first look at the exponent 0. Let's say we're trying to decide, right, how we should extend our definition of exponentiation to the expression 3 to the power of 0. We want to assign 3 to the power of 0 some quantity that makes sense. Now we know that whatever we assign this quantity, it should satisfy 3 to the power of 0 times 3, say, squared, equals 3 to the power of 0 plus 2 which equals 3 squared. Now notice that multiplying 3 squared by 3 to the 0 did nothing, right? That means that 3 to the 0 must be the thing that does nothing when you multiply it by it. And there's only one such thing, the number 1. So therefore, the only value that we can assign to 3 to the power of 0 that makes any sort of sense and preserves this existing pattern is 1. We're going to decide that 3 to the power of 0 is equal to 1. Now, this logic works for any base. So in general, we're going to decide that x to the power of 0 for any base is equal to 1. So now we're ready to answer our original question: how should we extend our definition to negative number exponents? How should we define 3 to the power of negative 5? Well, we know that whatever we define this to be, it should satisfy 3 to the minus 5 times 3 to the positive 5 is equal to 3 to the power of 0, which we decided before only makes sense to equal 1. Dividing out on both sides, we get that 3 to the minus 5 should equal 1 divided by 3 to the positive 5, or the reciprocal of 3 to the minus, or 3 to the positive 5, because this value is the only one that preserves our existing pattern of adding exponents. Now this logic works for any base and any negative whole number exponent. So in general, x to the minus y, or y is some whole number, is equal to 1 over x to the positive y. Anyway, I hope this way of extending exponentiation makes sense. That's all I had for you today, and see you all next time.